Okay, so now we've seen the construction of the electroweak braking sector from a rather modern point of view, and we've seen that the Higgs solution was absolutely not necessarily the only one, but really, even before the discovery, looked by far the simplest. And as I said, it is the simplest, but is not very satisfying from a theory point of view. And I will discuss what are these unresolved questions. However, here I want to pause for a little bit and go back to how the Higgs boson was introduced, because I think it's a year of celebration of the Higgs. I think it would be useful also to understand not just the perspective of the 2012 Higgs, but also what was the perspective when the Higgs was introduced. So in order to do this, we have to travel back in time and go to the early 60s, where the physics scene was indeed very different. Think of what was the scene? Well, weak interactions. Weak interaction. The story was not very different from the time that Fermi introduced its theory of beta decay in 1934. Of course, things had changed since that time because experiment, and in particular the very important experiment by Madame Wu of discovering parity violation, had narrowed down the structure of the Lagrangian into its modern V minus A structure. Then in 64, remember 64 is the year of the Higgs boson, just for the Higgs mechanism. So in 64 was also discovered CP violation, giving a new ingredient to the structure. Now, from today's perspective, the Fermi theory may look almost trivial, right? You have a process which is a beta decay, in which a neutron is converted into a proton, electron, neutrino. What is the most trivial thing that you do today? Well, you write down some contact interaction between these different particles, and here we go. Well, this was not trivial at that time. The concept was really revolutionary because Fermi applied to beta decay the ideas at that time were really emerging ideas of quantum field theories and how to treat electromagnetic radiation and absorptions in atoms. So in Fermi's view, the electron and the neutrino are emitted from nuclei in beta decay, but they're not part of the nucleus before. Exactly in the same way as the photon is emitted by an atom, but is not a constituent of an atom. And this was really a revolutionary concept. When Pauli introduced the idea of the neutrino, he introduced it assuming that the neutrino was a constituent of the nucleus, and he gave a small magnetic moment in order to interact with the nucleus and keep it inside. Instead, the idea here is really particle creation and annihilation, which is a quantum field theory concept. Fermi, in order to introduce this concept, had to invent a new kind of interaction, which is weak interaction. Incidentally, the neutrino, which is part of the story, was discovered in 1956 by Cowan and Reines in the famous experiment in the nuclear reactor of Savannah River. And this proved that the particle hypothesized by Pauli in 1930, just to fix the spectrum of the electron emerging from beta decay, was indeed a reality and not just a theoretical invention. Of course, it took a long time between theory and experiment, 26 years. It was really, in particle physics, it was unprecedented and was an example of the longest time. And when Reines and and Cohen discovered the neutrino, they sent a telegram to Pauli saying, we are happy to inform you that we have definitely detected neutrinos, blah, blah, blah. And then Pauli replied, always in his curt and sardonic style, saying, thanks for message. Everything comes to him who knows how to wait. 26 years was indeed a very long time. Incidentally, the discovery of the Higgs boson took 48 years, so we're really in a different time scale. Electroweak electromagnetic interactions. By the end of the 40s, this really marked, quantum field theory marked its most striking success with QED. The theory gave a brilliant explanation of all electromagnetic processes, including higher order effects, like the G-2 of the muon, like the Lamb shift, took care of all the infinities, and Nobel Prize came for that. But if electromagnetic interaction were the success of quantum field theory, strong interactions marked the failure of quantum field theory. Indeed, in 1934, the progress with strong interaction came from Yukawa, that understood that in the same way as the electromagnetic interaction are infinitely range because the photon is massless, given that strong interaction are short range, they act at a distance of a typical nucleus, then the carrier of the force, whatever it was, had to be massive. And Yukawa then computed the mass of this particle by this simple equation, by saying that the mass has to be the inverse of the radius, and found out 100 MeV. And so it predicts the existence of a particle, which today we call it the pion. At that time had lots of names. It was called the most common name was mesotron, but had lots of very curious and funny names. Of course, Yukawa was a very soft-spoken and reserved Japanese, always just called it the heavy particle. Never gave him a name. But anyway, that particle then was discovered very quickly. 1936, Anderson in the cosmic rays discovered a particle that has exactly the right charge as predicted by Yukawa and roughly the right mass. So this mesotron, or the pion, whatever you want to call it, has been discovered. This is funny. This is a lesson for experimentalists because it took some time. Of course, the war then was in between, and there was some delay because of that. But in some experiment, especially in the experiment by Conversi, Pancini, and Piccioni, it was found that this particle, the particle discovered by Anderson, could not be the pion. And the reason was because it did not have strong interaction, was not interacting very strongly with nuclei. And indeed, the pion was discovered again only in 1947, and this time was a real pion. The problem was that nature played a trick with physicists. There were two particles which had roughly the same mass, same charge. One is called muon today, the other is called pion. So maybe the Higgs discovered today is not a Higgs, is another particle. We will see. But at any rate, the discovery of the pion certainly did not solve the mystery of the strong force. In the 50s, in the 60s, the time we're discussing right now, lots of new particles were discovered, and strong interactions really seem beyond comprehension. People believe that quantum field theory could not give the right answer and started looking for alternatives, S-matrix, bootstrap, and so on. And even at that time, even the success of QED seemed less convincing to people because people were very scared of this process of renormalization, and it was taken as the evidence for incompleteness of the theory. It was just a mathematical trick. This misconception about renormalizability is something that stayed in physics for a long time, because until the 60s, people really gave to renormalizability the idea there was a fundamental property, and not the way that we look at it today as just an emerging property of an effective theory. And this has really played a role in the development of the Standard Model. But anyway, so even if people did not believe much in quantum field theory, there were still some pioneers. And a very important step was done in 1953 when Young and Mills showed that there is a non-trivial generalization of QED with multiple force carriers which self-interact differently than the photon. Of course, I'm talking about non-abelian gauge theories. But the way that was introduced was because they were viewed as a potential candidate of a theory of strong interactions, because we had this self-interacting force carriers. And actually, some people at that time dreamt to use it as an explanation of quantum gravity. So that was the idea of Young and Mills. A crucial point is that in a gauge theory, the gauge field transforms non-linearly. And therefore, a gauge symmetry forbids a mass term, because the mass term is not invariant under a non-linear symmetry. On the other hand, Yukawa has shown that the carriers of strong interactions had to be massive. So immediately after Young-Mills theory was proposed, there was this fundamental question: is it possible to deform a gauge theory in such a way that mass is allowed so that you could use it as an explanation for strong interaction? The problem is not trivial, because gauge symmetry removes the longitudinal degree of freedom. And for a massive particle, the separation between longitudinal and transverse polarization is not Lorentz invariant, as it's fairly obvious, because if you go in a frame in which the particle is at rest, then in that frame there's no direction of motion, and therefore you cannot distinguish longitudinal from transverse polarization, unless you break rotational invariance. So that means that there is a fundamental difference between the massless and the massive theory, because there are different degrees of freedom in the two phases. One cannot go, if you wish, continuously from the massless to the massive case, as the number of degrees of freedom are different, and the gauge symmetry eliminates exactly the longitudinal components which are needed to describe a massive theory. So the presence of the longitudinal polarization is necessary in a theory of massive gauge bosons, but we also seen that the longitudinal polarization causes a problem with perturbative unitarity. So superficially, this connection really seemed unescapable. Gauge symmetry was connected with the masslessness of the force carrier. Of course, people at that time knew that symmetries could be broken spontaneously. And so people try to think of the idea, because then you have multiplets, as we've seen, of different masses, but that didn't seem to help. Actually, people thought that made things worse, because in 1961, Boson proved his theorem, showing that the spectrum must necessarily contain a massless state, and no massless states were seen in strong interaction. So we're really having two problems. One is that gauge symmetry implied masslessness of the vector bosons, and on the other side is that if you try to break the symmetry spontaneously, you have massless scalars, and you don't want either of them. The funny thing is that when you put these two problems together, each one cures the other one. Now, the first one, who really understood that gauge invariance does not necessarily imply a massless force carrier, was Schwinger in 1961. In the abstract of this famous paper, he says, it is argued that gauge invariance of a vector field does not necessarily imply zero mass for an associated particle. So it spells out clearly. Of course, the analysis was based on consideration of currents, and there's no reference in the paper on the idea of spontaneous symmetry breaking. The first one who then understood the connection with spontaneous symmetry breaking was Anderson, which in 1962 writes a paper in which he explicitly spells out the idea of the Higgs mechanism already in the abstract, and it shows how the Goldstone bosons are eaten and the gauge field becomes massive. And this is stated, for instance, this quote from that paper that says, the way is now open for a degenerate vacuum theory of the Nambu type, meaning spontaneous symmetry breaking, without any difficulties involving either zero-mass Young-Mills gauge bosons or zero-mass Goldstone bosons. These two types of bosons seem capable of canceling each other out, the eating of the Goldstone bosons, and leaving finite mass bosons only. Of course, this did not have a relativistic system. It was inspired by superconductivity, so not the elements are there, but I think the idea is pretty clear. June 1964, there is a paper by Braut and Angler in which they show that the gauge particle in a fully field theoretical context, the relativistic gets, the gauge particle get a mass from spontaneous symmetry breaking. They work out both the abelian and the non-abelian case, but I was surprised when I read the paper. There is no mention whatsoever about what happens to the Goldstone bosons. So there's no mention that the Goldstone bosons are eliminated from the physical spectrum. Now, my interpretation is that Braut and Angler really had in mind a description of strong interaction. So they were focusing on having massive force carriers, because that's what they wanted to describe. Then there are two papers in July and August 1964 by Peter Higgs. Now, in my view, Peter Higgs was not, this is my interpretation, was not so much concerned about a realistic theory, say, of strong interaction, but mostly he wanted to address, show that there is a loophole in the Goldstone theorem. So contrary to Braut and Angler, that is a key of what I think Higgs is thinking. I wanted to show that the Goldstone is not present when you have local symmetry. So in this paper, in both papers, he studies only the abelian case. There's no reference to the non-abelian case. But he explicitly shows that the gauge boson becomes massive and that the Goldstone boson is eliminated. As I say, he writes two papers. The second paper, the one of August, is rejected by Physics Letter, by an editor from CERN. And so Peter Higgs sent the paper to Physical Review Letters, and then the referee, who, by the way, it was Nambu, accepts the paper, but suggests to Higgs to do a revision for 2 points he makes. One is that he points out a paper that Higgs was unaware of, which is the Braut-Angler paper. By the way, Nambu was also the referee of that paper, so he knew it. And then he also suggests, saying, well, you know, since there was this paper before, you should introduce new things. You should talk about this, make a comment about the mass spectrum of the theory. So Higgs then adds just one paragraph at the end of the paper. And this paragraph is this one shown here. There's no equation, no formula whatsoever, just a sentence. And it starts by saying, it is worth noting that an essential feature of the type of theory which has been described in this note is the prediction of incomplete multiplets of scalar and vector bosons. Of scalar, I said. So this is how the Higgs boson is born. However, there is a paper in 1966 in which Higgs explicitly solves the abelian model in the modern sense, and computes fully the mass spectrum. And you see it here, equation number 1 has, this is an abelian case, so as a gauge interaction, then you have a scalar with covariant derivatives, and then you have this scalar field has a mass term with a wrong sign, notice this is Lagrangian, and a quartic interaction. Then you go through the paper, you arrive at equation 24. I skipped the detail because I think you should know them. You end up with a theory which has the gauge field, a mass term for the gauge field, and then has one remaining scalar field. This is the Higgs boson, okay? Which has a kinetic term and a mass term with the right sign. So it's a massive particle. So now I give you a lesson to students who are starting their career, and you're always worried about publishing. They tell you publish or perish. This is all nonsense. You know how many papers did Peter Higgs publish after this one? One paper in 1979. You know what his H index is 5. However, he wrote the right sentence at the right time, and that's enough to get the Nobel Prize. So remember that next paper, don't worry about publishing too much, but write down the right sentence. This is not the end of the story. Still in 1964, Guralnik, Hagen, and Kibble obtained the same result that Broughton and Glare and show the decoupling of the Goldstone boson. At least they do it in a linear approximation in the field. I was a little puzzled when I looked at it, but so they have the Higgs boson there, but since they are working the limit in which the quartic coupling is 0, the Higgs boson is massless. So they have a massless Higgs boson. However, they show that this massless state decouples contrary to the case of the Goldstone. Then in 1967, Keeble generalizes the 1966 results of Higgs to the non-abelian case. So far, notice I made no reference to electroweak interactions. Really, the idea of spontaneous symmetry breaking, massive gauge bosons, was very intriguing. But people thought that if it had an implication, because nobody knew, had to be in strong interaction. It was only in 1967 that Steven Weinberg understood that people were trying to apply these ideas to the wrong type of interaction. The right place was the weak interactions. Now, the paper is called a model of leptons. Quarks already existed because the eightfold way dates 1961. However, the existence of quarks was still unclear. In particular, even many theoretical physicists did not believe it. They thought it was maybe some computational method. And anyway, the situation was unclear enough that Weinberg concentrates only on leptons and not on quarks. But all the conceptual elements of the Standard Model are there. You see that from the equations, so you have the, the notation is really like a model notation. You have the gauge or the gauge fields, the interaction. Notice that the covariant derivative of the Higgs field. Notice that for the first time, Weinberg also introduced the coupling of the Higgs to the leptons, to the fermions, showing that they can give mass. And here we go, the Higgs potential with the mass with the wrong sign for the Higgs. And with his usual clarity, Weinberg includes Higgs mechanism, weak interaction, explains the Z photon mixing, the Yukawa interaction for the masses, and you see here he derives the mass of the charged gauge boson. He talks about the mixing between the Z and the photon. He shows that the photon is massless and the Z is massive, and computes the mixing angle. However, it's surprising that this paper did not attract so much attention. If you look at the plot of the citations, it's really remarkable how few citations this paper got until 71, and then it grew. What happened in 71 was a proof of renormalizability. Again, renormalizability is a crucial element by TeV. Really, that changed how people view the Standard Model, and then you know the story of what happened next. So the story of the Higgs mechanism of spontaneous symmetry breaking is certainly fairly intricate, and as often the case in scientific ideas. It's very rare that scientific ideas have only one, the paternity, you can really define it to one person. And the reason why today we identify the Higgs mechanism, the Higgs boson, everything just with the name of Higgs is mostly due to Ben Lee. In 1972, so after the 12th revolution, in a summary at a lepton-photon conference, he talks about the successes of the Standard Model, and he starts calling the Higgs mechanism, the Higgs boson. He calls it actually the Higgs, in the same page. You see how many times he's mentioned Higgs. He talks about the Higgs scalar, Higgs meson, Higgsian scalar, all names for the same object, which is what we call it, the Higgs boson today. John Ellis once told me that he calls Ben Lee the Baptist, because he was the one who gave this name. Now, then the game became an experimental game. But many people, at least written in newspapers, say, oh, the Higgs was the most hunted particle for the last 50 years. I think it's really wrong. It's absolutely not the case, and the interest was rather recent. Why? Well, in an influential paper of 1966 by Ellis, Gaillard, and Nanopoulos, which was really a pioneering paper for the phenomenology of the Higgs boson, these authors conclude by saying, we do not wish to encourage big experimental searches for the Higgs boson, but we do feel that people performing experiments vulnerable to the Higgs boson should know how it may turn out. In other words, just don't do an experiment, look for the Higgs boson. But if you do other experiments for other reason, and you happen to be capable of seeing, why not having a look to the Higgs boson? This may look surprising today that after this paper in which you discuss the phenomenology of the Higgs boson, you conclude in this way. But I think it really reflects the way the people were thinking at that time. Because, for instance, in Iliopoulos, in Einstein Symposium of 97, writes, several people believe, and I share this view, that the Higgs scheme is a convenient parameterization of our ignorance concerning the dynamics of spontaneous symmetry breaking. and elementary scalar particles do not exist. Okay? So you understand that John L is saying that you should not do big experiment looking for the Higgs, tell people in CMS and Atlas, and then Iliopoulos saying elementary scalars do not exist. This is, however, was not an unreasonable point of view. It's just that out of the construction of the standard model, this Higgs potential looked just some toy construction, some parameterization of something that you don't know until some smarter theory should come up with a full description of the sector. I think things started to change in the 80s. Remember, 1980, inflation, so the role of scalar fields in physics is important. Supersymmetry in the 80s, the idea that the scalar fields now have a meaning as part of the fundamental theory. And indeed, in a prescient point of view, Okun, in a lepton-photon conference in 1981, he says, it seems to me that the problem number one of high-energy physics are scalar particles. The search for these particles is extremely important, mainly because of their vital role in symmetry breaking. Indeed, the first machine that had the Higgs search as one of its main tasks was LAP. Talking about 90s now, and LAP indeed played an important role in our understanding of the Higgs boson. First of all, it gave the important lower limit on the Higgs mass of 114 GeV. But equally important was the information the lab gave from indirect measurement. In the beginning, the Higgs mass was mostly a nuisance factor for the determination of the top mass, because people wanted to get information on the top mass from electroweak precision measurement, and since the dependence on the Higgs mass was only logarithmical, it was just not very important. But then, after the top discovery in 1995, then the game of electroweak precision measurement changed, and the idea was trying to infer the presence of a Higgs boson from those measurements. And indeed, there was a strong indication for a relatively light Higgs boson. This is a famous curve, and this is now where the Higgs boson mass lies. Then came the tevatron, which also had an important role, giving some bounds. But the story, of course, changes with the LHC. At the LHC, the production of the Higgs boson is mostly coming from gluon fusion. So two gluons emitted from the protons that merge into a Higgs boson. Now, this may seem strange, because after all, the Higgs boson was a particle supposedly related to mass. So its coupling has to be proportional to mass, and the gluon is massless. And the reason why it couples to the gluon is because, if you wish, the anomaly in the scale invariance, so that the coupling of the Higgs to two gluons is nothing else than the beta function. Or in other words, you can look at it in terms of a loop diagram of the Higgs that couples to the top, and since the top is a massive particle, you have a large coupling, and then the top which is a strong particle, couples to the gluon. However, there are also other channels which are very important for the Higgs production at the LHC. One is gauge boson fusion, in which you emit two, either W or Z, you radiate them from quarks, and you merge them into a Higgs boson. In this case, because you radiate them from quarks, you have two forward jets, which help you in the discrimination of the signal. Another channel is the radiation of the Higgs directly from a gauge boson line. And so here you have associated production of the Higgs boson and a W or Z particle. And then finally, another important channel is the Bremsstrahlung of the Higgs out of a top quark line. At the LHC, there's a large production of top quarks, and therefore you can exploit the large coupling of the Higgs to the top in order to produce it. Here, I'm showing in this plot the various cross-section as a function of the Higgs mass. Luckily, now you can just look at the 125 point, and you see that the importance of this channel are in the order that I was describing, but all of them play a role. This is very important because we are very lucky of the situation that various channels are simultaneously important at the LHC. And this, from a theory point of view, allows the determination of the properties of the Higgs boson in a fairly robust way. How does the Higgs boson decay? Well, as you know, that there are essentially two regimes. If the Higgs boson had turned out to be fairly light, then the dominant decay was a two-body decay into bottom quarks. If the Higgs boson had turned out to be heavier, then it's a two-body decay into gauge boson becomes more important. The reason is because the bottom Yukawa is a small coupling. And therefore, if you open the channel into two gauge bosons, you dominate. But if the mass of the Higgs boson is not large enough to produce on-shell two gauge bosons, then essentially you have one real, one virtual gauge boson, meaning that you have a three-body decay, and so you have a suppression, and this can compete with that. Well, 125 GeV, which is the mass of the Higgs discovered by LHC, happens to be exactly in the intermediate regime. And again, this is a very lucky situation, because if you have more decay channels available, you have the potential of studying the properties of the Higgs boson much better. There's also another decay channel which is very important, which is the Higgs into two photons. This comes from the same argument as the one in the two gluons. The difference is that here you have two different virtual particles that can contribute to the process. You can have a loop of top quarks or a loop of W bosons, because the W is a charged particle, so couples to the photon. It's clear that this effective coupling of the Higgs to two gluons or Higgs to two gluons essentially measure the existence of any particle significantly coupled to the Higgs, which is either electrically charged, in the case of the photon, or color charged, in the case of gluon. It turns out that this contribution is much larger than this one. It's about a factor of 7. It's much more important. And this has an opposite sign, so the top quark contribution reduces slightly the W. This will be very important when you compare the channel of the production of the gluon and the decay into photons. Here I'm putting a table of, you don't have to look at all these numbers. These are all the numbers that I'm summarizing here for the branching ratio, the cross-section of interest. But the reason why I'm putting it there is not that you memorize this number, but just to show you the variety of processes that can be measured at the LHC. So in particular, all these decay modes of the Higgs can and will be measured at the LHC, all of them except the charm, which is very difficult because charm identification is fairly poor in the LHC environment. But this means that we will have, and already have some of them, we'll have tests of the Higgs coupling to bottom quarks, to Ws, to Z, to gluons through the production, through photons, to top quarks, to tau, to muons, to an effective coupling of photon Z, and an invisible coupling, and a decay of the Higgs to invisible particles, neutrino or other new particles. So it's really remarkable, the amount of information that we can get from the experiment. If you are curious, you say, well, how do I get information of the Higgs decay into invisible? I mean, either you do it directly, or more interesting, you can do it indirectly. Suppose that, for instance, the Higgs particle has perfectly standard model decays, but also it exists a new particle, say a dark matter particle, couples to the Higgs, which then is invisible to detectors because it's very weakly interacting. Well, in that case, the branching ratio of the Higgs into any final state is given by the width of the Higgs into that final state divided by the standard model width plus the invisible width. Now, if you do it as simple arithmetic, you should show that this can be translated into branching ratio, standard model branching ratio of the Higgs into the final state, modulated by 1 minus invisible branching ratio. So by comparing the experimental information of the Higgs branching ratio with the standard model determination, you can infer information about possible invisible decays. So the story of the discovery of the Higgs boson is very recent. In winter of 2011, we had the first indications. Experimentalists could not call it discovery because we didn't have the famous 5 sigma required by law, but theorists are lawless, and so they already understood that the discovery was there. And indeed, rather than focusing on the discovery, they focused on anomalies. That's where theorists always look, something wrong, something to work on. And so with the first data, so these are the different channels compared with the idea of no Higgs, so 0 rate, or standard model rate, which is this green line. Okay? So you see that there is a significant evidence that you are closer to the green line than to the red line. But what were the anomalies? Well, theorists immediately noticed this large, very large rate. We're talking about a factor of 3 or so in the central value with respect to the standard model of Higgs into 2 photons. Then there was a low ratio of Higgs into WW with respect to Higgs into ZZ. You see, WW is fairly low, is below the green line, while the Z tend to be up. This was very interesting because this ratio is fixed by custodial symmetry, which is the same symmetry that I was showing you before that was playing a crucial role for the delta rho relation. So finding that the Higgs was not satisfying that symmetry would have really been curious and changed the story very much. And then also low rate of Higgs into 2 tau tau. Summer 2012, discovery, champagne bottles, newspapers, headlines everywhere, the Higgs has been discovered. And still, the theorists do not look at the discovery, but they just want to look at the deviation. So what happens to Higgs into 2 photons? Well, it went down significantly with respect to the previous winter, but it's still up. You see that the Higgs into 2 photons is still significantly above 1. We're talking about 2 sigma effect, so it's not something especially, so I'm taking away some of this question mark, but it was still there. However, the WW to ZZ ratio was dead on 1, and so that's it. And the Higgs into tau tau, if anything, got stronger. During this winter, more data have come out. What happened? Well, Atlas showed that H into 2 gamma is still up. However, CMS gave no update. So we are still waiting. The result will be very soon. This winter, probably in the winter conference, you will hear about it. This will be important. The Higgs into tau tau, which CMS was very excited about, went away completely. Higgs into tau tau in CMS, which is here, is perfectly equal to 1. This was a combination of statistics, I mean new data, and also adjusting calibration by the experimentalist. So the photon is still an open case. We will see. We will have this winter the final presentation of data from the 8 TeV run, and we will see what result is. But unless we get some surprise in the 2 photons, it's clear that the Higgs looks remarkably like a standard model 1. Also, notice that just the fact that the Higgs decays into 2 photons already tells you something. It tells you that it cannot be a spin 1 particle. And the reason is very simple, because a photon, as you know, has no longitudinal polarization. So that means that the spin has to be always along or opposite to the momentum. So when you go to the rest frame of the decaying particles, you can make a spin 0 or spin 2 particle, but you can never have a spin 1 particle. So the spin 1 particle cannot decay into 2 photons. Notice that the argument is not valid for the Z, because the Z is a massive particle and therefore has also a longitudinal component. So we learn it's not spin 1. Could that be spin 2? Well, experiments have already ruled out the hypothesis to 91%, looking at the distribution of the final state. Very soon will tell us that's not spin 2. It is not something that we are particularly excited. We are waiting about this information. A little more interesting is knowing the CP properties of this particle, because it could be that the Higgs is a CP odd particle and not a CP even, as predicted by the standard model. But the CP odd hypothesis is already excluded at the level of 99%. For instance, in supersymmetry or in any 2 Higgs doublet model, you would have particle with opposite CP properties, and so this is an interesting test. So that's it. Is that all standard? Should we forget about new physics? Well, let me just present just 2 glitches just for your information. So this is the famous CMS curve of the 2-photon invariant mass. And you see this is the background, and this is the prediction with the Higgs at 125. And here we go. This is the famous bump. It's so famous it's been blown up here in this region, zoom. This is a discovery. This is a Nobel Prize. Okay, but what's happening here? At this point, is this just a statistical fluctuation or not? Well, how large is the statistical fluctuation? And you can see it here. This is the significance of the various channels in CMS. The green line is the 2-photon significance. So you see that there's a big, big peak corresponding to 4 sigma, more than 4 sigma at 125. When you combine it, you get 6 sigma when you combine it with the other channels. But you get a little bump. Some theorists made a big fuss about this. We are still at the level of 2 sigma. We will see. Okay, so keep an eye. The other strange thing that was presented this winter comes from Atlas. So Atlas gave, you've seen it, things are coming okay, but then they are combining in this plot the information of the Higgs into 2 photons and the Higgs into 2Z. When I say 2Z, I mean one real, one virtual Z that decay into 4 leptons. And this is the result in a plot where the axes are the Higgs mass, horizontal, and vertical is what we call signal strength, which means the observed rate in units of the standard model prediction. So if you have a perfectly standard model result, you should get 1 and the value. The Higgs into 2 photons are the red ellipses, the data, and the Higgs into 4 leptons is the blue ellipses. Now, in the talk, they conclude that you can combine these 2 ellipses, and the combination is compatible at the 2.7 sigma. And the combination gives this black line, which gives a mass of 125.2 GeV. Notice that the errors on the mass now has gone below the 1 GeV level. So it's really impressive. It is impressive, but I mean, for a theorist, this is incompatible at 2.7 sigma because, I mean, this is not such a great compatibility. Is this just a statistical problem? Is it a problem of some calibration? Or is there some more complicated physics in it? I don't know. I'll leave you with that, but we'll soon receive the answer. But let's summarize what's happening. Well, I think that there's no doubt that the Higgs discovery has been a fundamental discovery in physics. Something that goes beyond just the borders of particle physics. We have identified the origin of a fundamental scale, the fundamental scale of weak interactions. We have also understood that part of the dynamics of a new way in which the gauge symmetry can be realized. We've learned something about the structure of space-time itself, because the Higgs vacuum is a property of the vacuum. And that's something that goes really beyond just particle physics. Is it some kind of new ether that we've discovered? Now you may argue, well, isn't that ether, wasn't that ruled out by Michelson and Morley experiment? It was, but this ether, the Higgs field, has a very special property, and the very special property is that it's Lorentz invariant, meaning that no matter in which reference frame you go, no matter how you move with respect to this medium, you're going to measure exactly the same quantity. This is, of course, a very counterintuitive thing, but it's relativity, okay? This is Lorentz invariance. And that's why no Michelson-Morley experiment will ever rule it out, because the idea there was really to rule it out as a result of the relative motion of the Earth with respect to the ether. We have also discovered a new force of nature. We always talk about the 3 forces, but the Higgs interactions are not QCD, are not electromagnetism, are not weak interaction. We have discovered a new force, but we still have to understand it, what it is. So in spite of this success, really we cannot say that we are at the end of the story. We are at the end of this lecture today, and I will devote the next 2 lectures on explaining what are the problems that are left unanswered by the Higgs and what could be possible explanations. Thank you.
Thank you, Gian. Are there questions? I do have one. How can they determine or exclude already if it's a scalar, spin zero, that it's CP off, it should be CPE.
Right. So again is the angular distributions. So because of it's what counts as the parity property, when you look at it, you have statistically different distribution. So if I just showed you the plot, what they're looking at the peak of they're looking at the distribution of some kinematical invariants that are sensitive to the parity property of the decaying particle. Then you can do a Monte Carlo, and depending on the CP positive or CP negative hypothesis, you make your prediction, which are two curves that has an overlap, but they peak on different points. And you look at the data, and then you have a certain separation. The statistical significance is not sufficient to rule out the CP odd hypothesis, but it will be by the Morion conference, most likely.